Then let's continue to do Bayesian inference with a Gaussian prior and a Gaussian likelihood. And we're going to make use of the fact that if you multiply two Gaussians, you get another Gaussian function. I'm going to do this just to slow down the pace a bit on my iPad. So there's a formula that is derived in Bishop's book, but also for the scalar case we derived it in the notebook. That if I have a Gaussian distribution, let's see, a Gaussian distribution over X, and the mean value is mu A, and the variance sigma A, and I multiply with another Gaussian distribution, also over X, and mean value mu B and sigma B, then I'm going to get some scalar, let's not call that A, well, let's call it A, times another Gaussian distribution, X, mu C, sigma C. So I get an unnormalized, if you will, Gaussian distribution. Now the mean mu C and mu and sigma C are given as follows. Sigma C minus 1 equals the sum of sigma A minus 1 plus sigma B minus 1. In other words, I can add the inverse covariance matrix, or add, if you will, the precision matrices. And for the mu C, we can say that mu C minus 1 times mu C equals mu A minus 1 mu A plus mu B minus 1 mu B. This is what you call the precision weighted mean. Sigma B to the power minus 1, the inverse variance is the precision, and we weigh the mean by the precision. So we can add precision weighted means or natural means, and we can add precision matrices. If we would have done this in natural coordinates or in the natural parameterization, then I could have written sigma C equals, lambda C equals lambda A plus lambda B, and eta C equals eta A plus eta B. So if we would do Bayesian inference, and that would be all that we would be doing, then often it's advantageous to use the natural parameterization or the canonical parameterization of Gaussians. But for now, let's just continue with the mean and the variance parameterization, the moment parameterization, because it's a bit more common. And I'm going to have this very simple problem. I have a parameter for constant theta, and I don't know its value. I make a measurement x equals theta plus epsilon. Epsilon is some noise, so I make a noisy measurement. And what do I know about this, about the noise? Well, the noise is distributed by a Gaussian, and that Gaussian has is zero mean and sigma squared variance. And in order to solve this problem, I also need a prior on theta. What do I know before I make this measurement? So I can say theta is also distributed by mu 0 and sigma 0 squared. So this is my model, and now the idea is I want to get a posterior estimate for theta after the measurement x. I want to make, just as an aside, a comment about notation. I write this, and I can also write this. The probability distribution for epsilon equals a Gaussian over epsilon given zero mean sigma squared. Whereas this first one here, I would read this as epsilon is distributed as a Gaussian, and that Gaussian has parameters mean zero and sigma squared variance. What I should not do is write something like P of E equals a Gaussian distribution, because I shouldn't do it like this, because this is a function over epsilon, but this function here, it doesn't have epsilon as its in its argument list. So that's the wrong way to do it. And in the same way, I also don't like to write it in this way. Epsilon is drawn from a Gaussian distribution. Well, I think it's drawn from a Gaussian distribution, and then we just give the parameters. The epsilon here is not needed. So this is something we don't prefer. The second one. So these two are equivalent. That's just a notational aside. But this is the system we work with. There is another way of writing down the system in exactly in a different way. Namely, I can say the prior for theta is a Gaussian distribution over theta given mu 0, sigma 0, and I have a likelihood for theta, px given theta, which is also a Gaussian distribution over x with parameters theta and sigma squared, which means that the probability distribution for x is a Gaussian over x with mean value theta and Gaussian noise with variance sigma squared. You can, if you look at these two distributions and you study them and you compare them to this set of equations, you compare it with this, you'll see that they are equivalent. The nice thing though is that this now is in the form of a prior over theta and p of x given theta, but that's actually a likelihood for theta because we have measured x. So we have now a prior and a likelihood. So we can just write down for the posterior, p of theta given x is proportional to p of x given theta, the likelihood, times the prior. And of course we have to divide by the denominator, but that's not going to be a function of theta, so I'm going to just drop that for now. So let's write this down. This is the Gaussian over x theta sigma squared times the prior for theta, which is the Gaussian over theta mu 0 and sigma 0 squared. So multiplying two Gaussians should give you a new Gaussian. The only problem is, note that this is a distribution over theta and this is a distribution over x. And that's unfortunate because if we look at the formula, here I have a distribution over x and here also a distribution over x, and then I get a distribution over x. However, there's a very nice thing that these two guys we can exchange because the Gaussian distribution is basically symmetric in its argument and in the mean. So this really is the same as p of theta given x, comma sigma squared times the Gaussian over theta, basically the prior mu 0 sigma 0 squared. And now I have a distribution, a Gaussian distribution over theta times another Gaussian distribution over theta. So I can write down what the posterior will be just by going to that formula. I get a new Gaussian distribution. Sorry, I'm not sure what this thing is doing here. So I get a new Gaussian distribution over theta with parameters mu1 and sigma 1 squared. The one meaning I've made one measurement this 0 meaning I've made 0 measurement, where 1 over sigma 1 squared equals 1 over sigma 0 squared plus 1 over sigma squared. Basically, I add the precisions to get the new precision, and the precision weighted mean is the sum of precision weighted means. And this is the answer, because now we have expressions. I can, with this expression basically gives me 1 over sigma 1 squared. I can fill that in here, and everything here on the right hand side we already know. So then I can get to know basically what mu1 is as well. So actually, so this is the final answer. There's an interesting rewrite though, and that goes as follows. If I now take the second equation and I substitute for 1 over sigma 1 squared, I substitute here this right hand side, I'm going to get 1 over sigma 0 squared plus 1 over sigma squared times mu1 is 1 over sigma 0 squared mu 0 plus 1 over sigma squared x. Now this I can of course rewrite as sigma squared plus sigma 0 squared divided by sigma 0 squared sigma squared. And if I take that now to the other side, I'm going to get mu1 equals sigma divided by sigma 0 squared plus sigma squared x plus sigma 0 squared divided by sigma 0 squared plus sigma squared mu 0. And I can rewrite this as mu 0 plus sorry, I think I'm making a mistake here. This should be a 0 and this 0 should go away. I think it's like this. Okay, so then I have mu 0 plus sigma 0 squared divided by sigma 0 squared plus sigma squared x minus mu 0. And this is an interesting way of writing the posterior mean, because this guy here, this is the prior for, so this is the prior. This guy here, this is x minus mu 0. If I don't make a measurement and I need to make a prediction about theta, I would have to go with mu 0, because that's the that's my knowledge actually about, aside from the variance, that is my let's say the best point predictor for theta, and x is the actual measurement. So this is the what we call the prediction error. This is a gain or a learning rate, and the whole thing is a correction. And the prior, of course, is also let's say the predictor for the measurement. So you can say that the posterior consists of some, let's say, a prediction before we make a measurement, which is the prior, then a prediction error, a reweighted prediction error. And the reweighing of the prediction error are ratios of variances. Basically, what we say, if sigma 0 is extremely large, that means I have a very large a priori variance. Basically saying my prior is so broad that it gives me no information. Then this factor here becomes close to 1, and my new mean will be very close to x. I'm going to put all my trust in x. On the other hand, if mu 0 is very small, that means I have very little variance in my prior, so I have a lot of precision in my prior, then one measurement is not going to make much of a difference. And this gain factor will be close to 0, which means that mu1 will be close to mu0. So it's the relative scaling of the variance in your prior and the variance in your likelihood that tells us how to weigh these two sources of information. In a certain sense, when you do Bayesian inference, when you get a posterior from a prior and a likelihood, you can kind of see them as equal partners. They are both, in this case, Gaussian, and it's the one that's going to weigh heaviest. It's just going to be determined is the one with the highest precision. And that's how that works. Okay, so but importantly, what we see here is because multiplication of two Gaussians leads to another Gaussian. It's unnormalized, but in the lecture notes you'll see an expression for this normalization term. But since that turns out to be a new Gaussian, therefore Bayesian inference with Gaussians, we can immediately write down the answer. Okay, and I'm going to do in the next video, I'm going to do another way of Bayesian inference based on conditioning and marginalization.